In this talk, we present VolRecon, volume rendering of signed ray distance functions for generalizable multi-view reconstruction. Multi-view reconstruction aims to estimate the dense geometry of a scene, given several posed images. Given n source views, the previous method first creates a global feature volume and then interpolates the SDF feature from it to do volume rendering. Differently, given one point on the epipolar line, our method first uses a view transformer to calculate the projection feature. We use a ray transformer to aggregate all the points on the ray. We call our method volume rendering of signed ray distance function because our distance function is view dependent. Combining the global volume feature and local projection feature, we achieve finer details than previous state-of-the-art SparseNeuS. Existing works on learning-based multi-view reconstruction have three main categories. The first is learning-based multi-view stereo, such as MVSNet. MVSNet warps source features at different depth samples to construct a 3D cost volume, regularizes it with a 3D CNN, and then regresses the final depth from the probability volume. Note MVSNet cannot render novel views. The second type is generalizable neural radiance field, such as IBRNet. Similar to NeRF, IBRNet first samples points on the camera ray to render. Then it projects sampled points to all views to retrieve multi-view features. It uses a ray transformer to aggregate points feature and outputs volume density and color of each point. Finally, it renders the pixel's color using volume rendering. The third one is the recently proposed generalizable neural surface reconstruction, SparseNeuS. Different from density field in NeRF, neural surface reconstruction adopts sign distance function and thus reconstructs smoother surfaces. SparseNeuS creates a 3D geometry volume by projecting grid points to each view and regularizes it with a 3D CNN. Then it decodes volumes feature using an MLP. To address the problem of having limited voxel resolution, SparseNeuS proposes a coarse to fine training process to boost performance. In VolRecon, we first construct a global feature volume as global shape prior. Specifically, we first divide the bounding volume of the scene into voxels with resolution k to the power of 3. The center point of each voxel is projected onto the feature map of each source view to obtain the multi-view features. This is done using bilinear interpolation, where the mean and variance of features across views are computed and concatenated as the voxel features. We then use 3D UNet to regularize and aggregates the information. After that, we use trilinear interpolation to get volume feature from the global feature volume. Given a pixel in the reference view, we sample m points on the ray emitted from this pixel. By projecting each point onto the feature map of each source view, we extract colors and features using bilinear interpolation. Then we apply a view transformer to aggregate the multi-view features into one feature, which we denote as the projection feature. To provide such non-local information of other points along the ray, we additionally use a ray transformer. We first concatenate the projection feature and corresponding volume feature into a combined feature to add global shape prior. After ordering the points in a sequence from near to far, the ray transformer applies positional encoding and self-attention on the combined feature to predict attended features. Then we use volume rendering of SRDF to render the image and depth map. Finally, we calculate render loss and depth loss. During our experiment on the DTU benchmark, our method outperforms the state-of-the-art generalizable neural surface reconstruction method, SparseNeuS. We report the quantitative result measured by chamfer distance and lower is better. Our method outperforms SparseNeuS on all 15 test scenes, as is shown in the table. Our method also outperforms neural surface reconstruction because it requires many images to fit the model, and generalizable neural surface reconstruction as it has difficulty in finding the surface. We refer readers to the paper for more details. Compared with MVS methods, ours is comparable with the classical MVS method CoMap and is slightly worse than the seminal learning-based MVSNet. Though our focus in this work is reconstruction, our method can also synthesize novel views. Here's the result of rendered novel views from 4 nearby input views. Besides the quantitative results, we also provide a visual comparison of reconstructed mesh comparing VolRecon and SparseNeuS. Our method reconstruct with fine details. Moreover, we compare the generalization ability of SparseNeuS and our method on the ETH3D benchmark. Our method reconstructs the scenes with higher completeness than SparseNeuS. Thank you for your listening.